Good evening, everyone. Welcome to Wednesday night's live stream. So we are Chem Help ASAP, and tonight's live stream we are going to be working calorimetry problems. Now, these problems involve heat and heat transfer, and we'll do a little enthalpy work as well. So, as always, have your calculators ready. Please post any questions you have, and we will get started and we'll just work through as many problems as we have. Okay, so let's start with our first problem. So we're going to start very simply at this point. We're going to do easier, kind of smaller problems, and then hopefully work our way up to more difficult problems as well. So let's read the problem first. It's always the first step. So we have a sample of nickel, and we are given the specific heat. We are told it is initially at 21.9 degrees Celsius, and it is heated to 84.6 degrees. We're told how much heat was transferred. That's 0.3118 kilojoules. And we want to calculate the mass of the nickel sample. So a couple of things before we start. I recognized this as a specific heat just because of the units. So joules per gram times degrees centigrade. Sometimes you'll see joules per mole times degrees centigrade. That is going to be either a specific heat or a molar heat if it's in moles. Also notice this is in kilojoules. So again, I mean, the problem specifies that that's heat energy, but anytime you see joules or kilojoules, you're automatically thinking, okay, this is energy. We're adding heat. What's going on with this? All right. So when we have this kind of problem, I like to write down the equation that we are going to use for this. So let's get that up. So when we have heat and we have a sample and we're changing the temperature, so this is not a phase change, this is just a temperature change. Our general equation is Q equals MC delta T. Now let's talk about what each of these variables are. Q is your heat. It is going to be measured in joules. It can also be measured in kilojoules. M is your mass of your sample. C is your specific heat. And delta T is your change in temperature. Now delta T more specifically is going to be your final temperature minus your initial temperature. That should be a dot over the I. So that is how we calculate delta T. Now, in general, if you have an exothermic reaction, your Q is going to be negative, and an endothermic, your Q is going to be positive. But often in these kind of problems, you don't necessarily have to worry about the sign. Like this one, we're trying to calculate the mass of nickel, so we don't necessarily need to worry about the sign in this problem. However, we will see problems later on where we will need to think about heat transfer and the sign of Q. But let's go ahead and let's calculate what the mass of this nickel is. So I am just going to plug in what I know. So I know Q because I was given the amount of heat energy that was put into this system. So that was 0.3118 kilojoules. M is my mass. That's what I'm trying to find. So I will just continue to call that M. C is my specific heat, which I was also given in the problem. So I am going to put that in as well. 0.444, and that is joules per gram times degrees Celsius. And then my delta T, again, is my final temperature minus my initial temperature. So it was heated to 84.6. That was my final temperature. Minus my initial temperature, it started at 21.9 degrees Celsius. All right, let's take a look at what we have written here. So we've got some good things and we've got some potential problems. I always like to look at my units before I start jumping into putting things in my calculator and working through all the math, because I hate to work through all the math and then realize that my units are messed up or I've made a mistake and then I have to go back and do it again. So what I see here is my specific heat is in joules, but my Q is in kilojoules. So that is a problem. I am going to have to fix that. Of course, I'm solving for my mass, and my mass is given in grams, so that's fine, no problem. And I have degree C for my specific heat, but I also have degree C here for, sorry, talking is hard tonight, degrees Celsius here for my change in temperature. So it looks like most of my units are matching. I'm just going to need to fix this joules to kilojoules. Now, I can change either one. It doesn't matter. They just have to match. I'm going to convert this kilojoules on the left-hand side into joules. So let's do that. So this is going to be 311.8 joules. And again, my mass is still just M because I am solving for that. My specific heat. I should point out that my degrees Celsius here is in the denominator of this unit. So it's joules over grams times degrees Celsius. It's sometimes just written a different way. And when I finish writing this out, I'll show you the other way sometimes you might see it. Degrees C. So I'm going to change colors. So this specific heat is written with a slash to mean a divided by, but sometimes you might see it written like this, where you have joules, grams to the -1, and degrees C to the -1. So it can also be written with the units like that. Again, all that means is your grams and your degrees Celsius are in the denominator. So it really doesn't matter, just as long as you know what both of them mean. All right, so let me double check my units. So joules and joules are good. Of course, my mass is going to come out in grams, which is perfect. This is going to give me degrees Celsius, and I've got degrees Celsius here. So now I'm ready to plug and chug into my calculator. So solving for mass, I'm going to get a mass of 11.2 grams. And again, I just worked through the algebra here. Make sure that when you're doing the algebra that you do this calculation first. It is in parentheses, and you don't multiply this by that. And then, just follow your, PEMBAS rules for your algebra. So that was our simple problem. This is our first calorimetry problem. Again, it's a pretty easy one, but it's nice to get going with what are the variables, what do they mean, what are the units, how does this all work? Okay, any questions? Doesn't look like there are any questions, so let's go ahead and move on to our next problem. All right, so a 165 gram sample of copper, again, it's nice to get the specific heats, is heated to 76.4 and placed in a container of water at 24.3. The final temperature of the water and copper is 27.9 degrees Celsius. Okay, that makes sense. So we heated up copper pretty hot. We threw it like in a cup of water, and the water warmed up. So we want to know what is the mass of the water, and we're assuming no energy is lost to the environment. So this is a very common thing. Sometimes the problems will say this was done in a calorimeter, or sometimes a coffee cup calorimeter, but you assume that you haven't lost at least a significant amount of heat to the environment. Now, of course, in real life, you do lose some heat to the environment, but this is going to simplify our equation tremendously by assuming that there is going to be perfect heat transfer from this hot sample of copper to the water. So we assume all the heat from the copper is transferred to the water perfectly, and we haven't lost any to the environment. So what this means is that the heat lost by the copper is going to equal the heat gained by the water. So we don't have to take into account any other things. So this means that the heat of the copper will equal the heat of the water. Now, here is where we need to take into account heat lost versus heat gained, exothermic versus endothermic. So because one thing, the copper is losing heat, and another thing, water is gaining the heat, one of these needs to be a negative sign. Now, it doesn't matter which one you make negative. I tend to make the metals negative, and I tend to write them on the left-hand side. So I'm going to put a negative in front of the copper so that the heat lost by the copper, that's the negative, is gained by the water. And this is what is going to make the algebra work, especially as we get into other problems. Okay, now my Q's are the same as before. It's just MC delta T, but I want to be careful that I keep straight what data goes onto the copper side and what data goes to the water side. So my Q of copper, I'm going to write as my mass of copper times my specific heat of copper times my delta T of copper. And the same thing here with the water. You want to use the mass of water, the specific heat of water, and the delta T of water. So a very common mistake that I see students make when they do these kind of problems is they'll flip-flop something, like instead of putting the specific heat of copper here, they'll put it over here just because it's easy to get lost in these details. But you really want to make sure that you keep all the information about the copper with the copper and all the information about the water with the water, because again, you hate to work through all of the math and all the algebra and oops, you've put the wrong number in the wrong place. So that's why I like to use subscripts. However it works best for you to keep track of what's going where. All right, so let's put some numbers in. And this is going to take a little bit of space. So there's my negative on the outside, and I'm going to use brackets because I'm going to deal with the negative in a bit. So I need my mass of copper. That was 165 grams. I need my specific heat. Again, make sure you pull the specific heat of copper and not the specific heat of water. So the specific heat of copper is 0.385 joules per gram times degrees Celsius. And then again, my delta T, again, remember delta T is T final minus T initial. So my final temperature here is 27.9 degrees Celsius. Minus, again, be careful, you want the initial temperature of the copper, and that was 76.4 degrees Celsius. Okay, and I'm going to close my brackets. So that is all my information with the copper, and now I need to put in all my information with the water. So the mass of water is what I'm looking for. So I will just keep this mass of water. My specific heat, again, make sure you pull the specific heat of water, is 4.184 joules per grams times degrees C. And I'm going to have to squeeze this in a little bit. Okay, so again, my final temperature is still 27.9 degrees Celsius. And again, I want to pull my initial temperature of the water, and that was 24.3. Okay, I'm going to kind of squeeze that in. I did not write my units there. All right, so now that I have all of my numbers in, now I can calculate what my mass of water is. So what I've got is, this is going to be 3080.96 joules, and that is going to equal mass times 15.0624, and that is joules per gram. Okay, so remember, I'm already canceling units out here. You can see my grams cancel, my Celsius cancels. Again, here my Celsius is going to cancel. So that's where these units come from. And so my mass of water is 205 grams. Okay, so that is the mass of water. All right, let's make sure there aren't any questions. Nope, no questions. All right, fantastic. Now, one thing I will say, if you get stuck, especially with these negatives floating around, and let's say you had a negative mass, well, you would know that there's no way you could have a negative mass. It probably means you just have one too many negatives. Just make it a positive. That's totally fine. Okay, let's go on to this one. A 56.7 sample of lead. Okay, we got the specific heat. All right, so we're taking another metal, we're heating it up really hot to 95.4, and then we're placing in a calorimeter that contains 75 grams of water. Okay, we got the specific heat, and we've got the water's initially at 19.6, and we want this time, so we want to calculate the final temperature of the metal and the water. So again, this time we've taken lead, we've taken a piece of lead, we've heated it up really hot, we've put it in some water. The heat is lost by the lead and gained by the water. Again, we're in this one problem specified that we're in a calorimeter. So that means, again, we're going to assume that we haven't lost any heat to the environment, that the heat transfer from the lead to the water was perfect. So we're going to set our Q's equal to each other. And this time we're solving for our final temperature. Okay. So I'm going to say the heat lost. Whoops, I forgot my P for lead. The heat lost by lead is going to equal the heat gained by water. Again, especially mathematically, it makes no difference which one you make as the negative. I just tend to always put it on the left with my metal. I guess I've gotten into a habit of doing that. All right, so now that I've got my Q's, I'm going to change this up and write in my mass of lead, my specific heat of lead, and my delta T of, of lead, and that's going to equal, again, my mass of water, my specific heat of water, and my delta T of water. Again, it's really important that we put all of the information with lead on the side with lead and water with water. It's so easy to get these things flip-flopped with all of these numbers floating around. Okay, let's keep going. Let's actually put some numbers in. Okay, so my mass of lead is 56.7 grams. My specific heat is 0.128 joules per gram times degrees Celsius. And my final temperature, I do not know. That's what I'm trying to find. My initial temperature, again, of lead is going to be this 95.4. Okay, and now let's do the water side. So my mass of water is 75 grams. My specific heat is 4.184. And again, for my delta T, I do not know what my final temperature is, but my initial temperature for my water is 19.6. Let's do a quick unit check before we work through this algebra. So, okay, grams, Celsius is going to be fine. Yes, Celsius is going to cancel. Great. Okay, so all of my units are matching, although the Celsius doesn't quite totally cancel yet because doesn't absolutely work out. For this problem, I am not going to carry the units forward just because I've checked them out and the units get a little funky with us. And I think that's unfortunately going to add some extra confusion. So I'm just going to work through the math at this point. So what I've got on the left is 7.26 times my final temperature minus 95.4. Oops, that decimal kind of disappeared. Oh, you know what? I should change that to a bracket so it makes it a little more clear. And then on this side, and there is my final temperature minus 19.6. One thing I guess I didn't point out that I should mention is the final temperature here is the final temperature for both of them. So that is the same variable. So it almost looks like we've got two variables in one equation, but that TF is final for both the lead and the water, so it is actually the same variable. Okay, let's keep slogging through this here. So we're going to carry this negative through. And the algebra does get a little tedious, but it will work out at the end. This is why it's important to have good algebra skills when you go into chemistry, because you want to be focused on learning the chemistry and not the math with the chemistry. That can make things very difficult. 321.1. Okay, so combined like terms here. And then solving for the final temperature is 21.3, and that is degrees Celsius. Again, just because working through all the math makes the units really funky, I just dropped it for simplicity's sake. But that is our final temperature. And I always like to do a does it make sense check. So if I have a final temperature of 21.3, that should be warmer than my initial temperature of water, right? So the water should heat up a little bit. And yes, you can see the water started at 19.6 and it heated up to 21.3. And also my lead started hot. It should be cooler, and it started at 95. And yes, it cooled all the way down to 21.3. What I think this problem also does a good job of illustrating is just the massive heat capacity of water. So you can see the heat capacity of these metals is really small, and you've got water over here with a heat capacity of 4.184. This is why if you're like boiling a pot of water for pasta or rice or, cooking anything, it seems to take forever to heat it up. Well, because you've got to put a lot of heat energy in because the heat capacity is just so high. But it means it takes a long time for it to cool down. So it's difficult on one end and better on the other end. But yes, water just has a super massive heat capacity. Okay, I am on kind of a tangent here. Let me make sure there are no questions before we move on to the next one. All right, let's go ahead and go on to the next problem. All right, so we have a 5-gram sample of aluminum pellets, okay, and a 10-gram sample of unknown metal pellets are heated to 100 degrees C. The mixture of hot metal pellets is dropped into 19.4 grams of water at 22 degrees Celsius. The final temperature of the mixture is 29.8. Identify the unknown metal. Okay, and we have a little table here of the different heat capacities of metals. And so hopefully when we solve for the heat capacity of metal, we'll be able to identify what metal it is. So this is kind of an interesting problem here because the heat of our metals is going to be transferred to the heat of the water. So now instead of just having one pure metal transferring heat, we've got to take into account two different metals that are transferring heat. All right, so let's think about our Q's and how the heat transfer is happening. So the heat from our metals is going to equal the heat transferred to our water. So I'm going to kind of break that down a little farther. So instead of just writing the heat of the metals, I'm going to be more specific. This is going to be the heat of the aluminum plus the heat of the unknown. I'll just call that X. And that is going to equal the heat absorbed by the water. Okay. I feel like once I get my Q set, it really helps me then move on to my MC delta T's. At least that's, again, how I like to do it. Okay. So the heat of the aluminum. So that's going to be the mass of the aluminum, the specific heat of the aluminum, and the delta T of the aluminum, plus the mass of our unknown, the specific heat of the unknown, and the delta T of the unknown. And that equals the mass of our water, the specific heat of the water, and the delta T of the water. So this is a little bit longer equation, but hopefully, again, you can see the similarities between the previous ones that we have done. Okay, I think we're ready to put some numbers in, so let's put some numbers in. I am going to have a lot of parentheses here. Okay, I think I'm going to switch this outside one. That's a terrible bracket. 2 brackets. Okay, yeah, that's passable. All right, so the mass of our aluminum is 5 grams. The specific heat of the aluminum is 0.903. And our delta T of our aluminum, let's see, our final temperature, here's the final temperature of the mixture is 29.8 degrees Celsius. Minus our initial temperature of our aluminum. Okay, so both the aluminum and the unknown metal are heated to 100. So this is 100 degrees Celsius. But this is going to be long. This is probably going to stretch over. Okay, so that's our aluminum. Now I'm going to do our unknown metal. Let's see, our unknown metal we have 10 grams. We don't know our specific heat. That is what we're hoping to find, because if we know the specific heat, then using this table, we should be able to identify it. And then our final temperature minus the initial temperature. Okay, that's that. And end brackets, and that equals our water. So our water is going to have to go underneath. So our mass of water is 19.4 grams. Our specific heat is 4.184 times degrees Celsius. And our delta T, so again, our final temperature of the mixture was 29.8, and our initial temperature of our water is 22. Okay, we got some algebra to work through here. Okay, so now this is going to look a little bit odd because you can see we've got a negative here. But trust me, everything works out in the end. Times RCX. All right, and then this equals 633.123 joules. All right, let's just keep on going. So I'm going to do some combining of like terms. So this is going to be 702. Oh, you know what? I'm sorry, I skipped my units over there. That's grams times degrees Celsius times our unknown specific heat. I am, moving through the algebra fairly quickly just because I'm running out of space and we've got other problems to do. Okay, so our specific heat of our unknown metal X is 0.450. And you can see how your units end up being joules per gram times degrees Celsius, which is always nice. Okay, so let's find, we don't have it exact, but do we have something close? We have something very close. So you can see iron here. So our unknown metal is iron. So sometimes as you're working through these problems, again, you might not get the exact answer, but this is certainly close enough to identify our unknown metal as iron. So this, again, was a lot of algebra, and it's easy to get lost in it, especially with the negatives and such. Again, this is why it's helpful to have your algebra skills down and you're comfortable with them before you start learning the chemistry on top of it. Okay, let's make sure there are no questions before we go on. Okay, I'm not seeing any other questions. Let's go on to our next problem. That one was kind of a long one. All right, so now we're switching gears a little bit. We're talking about reactions. So let's just go ahead and read the problem. So in a calorimeter, we have 50 milliliters of a 0.1 molar solution of silver nitrate and 50 milliliters of a 0.1 molar solution of hydrochloric acid. And we have mixed them. Here is our net ionic equation. So we're making silver chloride. If the two solutions are initially at 22.6 degrees, after the reaction is complete, the final temperature is 23.4. So we want to calculate delta H, and that's in kilojoules per mole, for the reaction. So we are calculating enthalpy here. Now, we are going to assume that the solution has the density and specific heat of water. That is a really big help because that is going to simplify things for us. Again, we are in a calorimeter, so we are going to assume that no heat is lost to the environment, so we don't have to take that into account. All right, so this is where we're going to bring Q into calculating enthalpy or delta H. Now, when I'm doing these problems, again, I always like to focus in on units. When I see the units for delta H, I think kilojoules, that should be able to come from some kind of Q calculation. And moles, I'm going to need to find moles for this specific reaction. So I'm kind of thinking a little bit stoichiometry here. But first, let's focus on getting the heat, looking at getting the kilojoules. All right, so we already know how to calculate Q. We need the mass, the specific heat, and the change in temperature. All right, and we'll call this Q of reaction. All right, to find our mass, well, we aren't given anything in grams, so it's not like the previous problems where we were heating up a chunk of lead, right? But we definitely have a mass to this reaction, and the mass is coming from the two solutions that are mixed. So I have 50 milliliters of the silver nitrate and 50 milliliters of the hydrochloric acid. So those volumes are actually giving me my mass. So what is my mass for 50 milliliters of both of these solutions? Well, this is where being able to assume the solution has the density of water means that the 50 milliliters from the silver nitrate solution is 50 grams. And then the 50 milliliters from the hydrochloric acid solution is also 50 grams of solution. So I am dealing with a total mass here. So I'm going to add these two together. So I have a total mass of 100 grams. Okay, so this is 100 grams. My specific heat, again, my problem said that I could assume the specific heat is the specific heat of water. So that is a simple plug and chug. And then my change in temperature. So I have a final temperature of 23.4 degrees C. I'm kind of running into my side calculation here. Minus an initial temperature of 22.6 degrees C. Okay, I have all my numbers in. I can actually calculate my Q for my reaction. All right, so my Q for my reaction is 334.7 joules. Okay, that's fantastic. So I already have the heat for my reaction. Now I need to worry about this moles right here. So I've got amounts of my reactants, of both reactants. And that makes me think of limiting reagent. I know everybody groans as soon as I say that. Let's switch over to color here. So let's first, if we're going to do any kind of stoichiometry, whether that's limiting reagent or simple stoichiometry, we need to know moles. So let's figure out moles of silver nitrate and moles of hydrochloric acid. So I will do this reaction over here on the left. Now these are given in molarity. So if you remember, molarity is simply moles of solute over liters of solution. So I can calculate how many moles of silver nitrate I have and how many moles of hydrochloric acid I have. So for silver nitrate, my concentration is 0.1. And I am getting moles, and that is over liters of solution. Now, be careful, that's liters of solution. They gave me milliliters. So just make sure you do a quick conversion here to liters. And that is going to give me 0.005 moles of silver nitrate. Okay, so what hopefully you see here is I have the exact same numbers for hydrochloric acid. I'm going through the exact same calculation. That means I have 0.005 moles of hydrochloric acid as well. So I've got this same number of moles. Now let's double check because we are given a net ionic equation. So I've calculated moles of silver nitrate, but how many moles of silver ion do I have? Okay, so if silver nitrate is dissolved in solution, I'm going to get silver ions plus nitrate ions. And these are in a 1-to-1 ratio. So that means if I have 0.005 moles of silver nitrate, I have 0.005 moles of silver. So I'm going to write that above the equation. Now let's see what happens with the chloride that's coming from the hydrochloric acid. So what happens when HCl goes into solution? That doesn't really start as a solid. Maybe I'll put that as a liquid. Usually it comes as a concentrate. That is going to give me protons plus chloride ions. Again, if I have, I'm going to have to really squeeze this in down here, 0.005 moles of hydrochloric acid, I'm going to get the same number of moles of chloride ions. Again, it's a 1-to-1 ratio, which means this is also 0.005 moles. So what I'm seeing here is that both of these are limiting reactants. So they are perfectly in a 1-to-1 ratio. So it really doesn't matter which one is limiting. They're both going to run out at the same time, which means my number of moles is 0.005 moles for the reaction. That really makes my life a lot easier because even though I had to kind of think about it, it makes the math really easy. So let's go back to calculating delta H. So to calculate delta H, I'm going to need the kilojoules of heat over the moles of reaction. So I'm almost there, right? The one thing I need is this is in joules, so I do need to convert that into kilojoules. So let's just do that very quickly. Oops, that is kilojoules. And I already have my moles, 0.005. So let's plug our numbers in. All right, and that is going to be divided by 0.005 mole. So I get an enthalpy of 66.9 kilojoules per mole. Okay, so here is where, depending on your teacher or your professor, you may need to decide what sign you need to assign this reaction. So remember that exothermic reactions have a negative delta H and endothermic reactions have a positive delta H. So for this reaction here, are we endothermic or exothermic? Well, our temperature went up. We gave off heat. That is exothermic, which means I need to put a negative in front of this delta H. Again, for these sign conventions, wherever possible, I like to push that to the very end and not worry about it until I've done all my calculations. And then I think, okay, is this an exothermic or an endothermic reaction? All right, this was a good problem. It brought in a lot of different concepts into calorimetry, especially having to pull in your stoichiometry and your concentrations and all of that kind of stuff. Let's make sure there are no questions before we go on to the next problem. Okay, this is going to be our last problem. And yes, okay, good. We've got enough time for it. So we've got another reaction to work with here. So again, we're in a calorimeter. We've taken 1.6 grams of ammonium nitrate and we have mixed it with 75 grams of water and the initial temperature is 25 degrees Celsius. Okay, so here is again our net ionic equation. After the salt dissolves, the temperature of the solution is 23.34. So again, we want to calculate our delta H in kilojoules per mole. And we're still going to assume the solution has the density and specific heat of water. So again, as you saw before, that's going to make our calculation a lot easier. All right, so we need kilojoules and we need moles. I'm going to focus on the kilojoules first. So I want to know what heat was either evolved or absorbed by this reaction. So I need my trusty Q equals MC delta T. All right. Now, just like before, we have to kind of think about our mass. So we have a mass of ammonium nitrate and a mass of water. These two masses are added together. So my total mass is going to be my 1.6 grams of ammonium nitrate plus my 75 grams of water. So that is my total number of grams, 76.6. Okay, my specific heat, again, the problem told me that I could assume I have the specific heat of water, which is always very nice. And now I need my temperature change. So let's see, my final temperature is 23.34 and my initial temperature is 25. Okay, I can calculate my Q. All right, so my Q for this reaction is 532.02 joules. And I remember that I had to convert that to kilojoules. And again, your delta H is in kilojoules. So let's just go ahead and convert that to kilojoules because why not? Okay. So that is my heat of my reaction in kilojoules. Now I need to worry about my moles. All right, so the moles for this reaction, this is definitely not any kind of limiting reactant because we only have one reactant. So really what I need is I need my moles of ammonium nitrate. Well, that's actually going to be pretty simple because I have my grams of ammonium nitrate. So let's just go over to the left-hand side here. So I have 1.6 grams of ammonium nitrate. And let's convert that into moles. So I just need my molar mass, which I have. And so I am going to get 0.019989. This is moles of ammonium nitrate. Okay, great. This one was actually easier to figure out moles than the previous one. All right, so now I'm ready for my delta H. I am going to do my kilojoules divided by my moles. So that is going to be my 0.53202 kilojoules divided by my 0.019989 moles. And that gives me a change of enthalpy of 26.6 kilojoules per mole. And again, I just kind of ignore my sign conventions until the very end. And I think, okay, is this an endothermic or an exothermic reaction? And you can see that we started at 25 degrees C and we ended at 23. So this was definitely a reaction that cooled down. It is endothermic. It is absorbing heat. So I will keep this as a positive number, a positive 26.6 kilojoules per mole. Okay, let's make sure there are no questions. There are no questions. Fantastic. I hope you found this live stream helpful with all of these calorimetry problems. As always, feel free to email me if you would like to see any kind of specific problem work. I'm happy to do anything. And thank you very much for tuning in. And we'll see you next week. Bye.